Welcome to Lecture 20, in which we will continue our discussion about the implementation of unitary transformations. Let's suppose, well, first of all, we will consider several examples of unitary transformations of 2-qubit states. So, following the procedure from last time, we know that for each one of these, the first step will involve arriving at a gray code that will give us a renumbering of the standard basis for 2-qubit states. And since in the end we're going to tie all of these examples together, I want to use the same basis for all of these examples. So I'll just say step 1 for all of the examples. And again, this is the step 1 referred to in Lecture 20, which is to find a gray code that will help us to determine the ordering of the basis for these problems. So, again, as we said before, we could start anywhere, but I'll just start with 0001 and then 0011 0010, and let's actually have 0000 as the first. I'll start with that one. So 0000 is the first one, 0001 is the second, 0011 is the third, and 0010 is the last one. And you can see if you check any two of these lists, they differ only in one position. So this is a gray code. And what this tells us then is that we will actually, I'm sorry, we just have a 2-qubit state here. So here we go. Here's our 2-qubit states, 0, 0, 0, 1, 1, 1, and 1, 0. And if we order them in this way, then we have a gray code. And so and this is just like the example we did before. Then we will associate with the state. And let me go ahead and put these to make clear that these are states. So we will associate with the 0, 0 state the vector 1, 0, 0, 0 transpose, and with the 0, 1 state we will associate 0, 1, 0, 0 transpose. With the 1, 1 state we will associate the vector 0, 0, 1, 0 transpose, and finally with the 1, 0 state, we will associate the vector 0, 0, 0, 1 transpose. So all of these vectors on the right-hand side there are really the transpose of row vectors, so they are in fact column vectors. Now, for the first example, we want to implement a transform that will take 0, 0 to A 0 plus B 1. Now, that is the only information that is given. So this means that we're free to choose how this transform acts on other states. We want to make sure that it is a unitary matrix, and notice that when we put this in terms of vectors, what we're saying is that 1 0 0 0 is being mapped to A times 1 0 0 0 plus B times 0 1 0 0. So we can see that only two of the components of the vector 1 0 0 0, only two of those components are being changed. And so since that is the case, if we choose the rest of choose the way that the transform affects the other states, we can guarantee that this will turn out to be a two-level unitary transform. And of course we know very well how to implement those. So for the let's choose the following. We'll call this perhaps U1. And we'll say then that U1 of 0 0 is equal to A times 0 0 plus B times 0 1. And U1 of 0 1 is equal to B times 0 0 minus A times 0 1. U1 of 1 1 is equal to 1 1, and U1 of 1 0 is equal to 1 0. And notice that I've listed the action of U1 upon the various states in the same order that those states are in the basis. And so we see that the matrix for U1 would be A, B, 0, 0, B minus A 0 0 0 0 1 0 0 0 0 1. And once we've written down that matrix, it's very easy to see that this is indeed a two-level unitary matrix. It'll be unitary provided that the square root of the magnitude of A squared plus the magnitude of B squared is equal to 1. So we do need to stipulate that, but as long as that's true, then U1 is a two-level unitary transformation. And let's go ahead and now do step 2 and step 3 for this example. So step 2 is to find a gray code that connects the first non-trivially transformed vector with the second non-trivially transformed vector. But notice that that is already done, because the first non-trivially transformed vector is 0, 0, and the last one is 0, 1. So we're already done, because remember, in this procedure, what we will do is come up with controlled NOT gates that will transform the first of these states into the next to last of these states. But the first state is already the next to last state in this case, and therefore we're already done. We don't need any of the controlled NOT gates in this case. All we would have is the following. Now, let's think about, okay, you can see that in this case that the U tilde matrix here is in the upper left-hand corner here of U1, and it would be this matrix A, B, B, minus A. And so we need to figure out on what bit will it act and what is the corresponding basis. Okay, so the answer is, since this list and this list differ in the second bit, then this will act. So I'll say U1 tilde equals A, B, B minus A. And that will act on the second bit, and we only want it to act on that second bit when the first bit is equal to 0. So we put a hollow circle up there, and then we'll have this. And now we need to figure out, or we want to figure out the how this acts, because we'd like to find the matrix for this. We'll see why later, but we want to guarantee that the matrix for this will match the matrix U1 that's given. And so let's check that to make sure. Okay, so if we have 0, 0 entering, let's check and see where that would go. Well, since we have 0, 0, the first bit is 0, so that will, in fact, we can go ahead and write 0, 1, 1, 0, 1, 1. In every case here, the first bit will be undisturbed. So we have 0, 1, 1. And likewise, when the first bit is equal to 1, nothing will happen to the second bit, because this is a controlled NOT gate where the first bit needs to be 0. And so when the first bit is 1, nothing is going to happen to either bit. So 1, 0 will go to 1, 0, and 1, 1 will, oh, and let me skip and do one thing differently here. Again, let's keep this same ordering that we have for our basis. And so instead of doing 1, 0 first and then 1, 1, I'll do 1, 1 and then 1, 0. But it still is the same reasoning. Whenever the first bit is 1, the second bit will remain unchanged. So 1, 1 will go to 1, 1, and 1, 0 will go to 1, 0. But now we need to figure out about 0, 0 and 0, 1. And remember that this is that occasion where we have to look, and we know that the U1 tilde matrix is given by this, but we need to find what the basis is there for just that one qubit. And the way that we do that is to look at the gray code, and here we're going from 0 to 1. So we'll have the standard basis here. This will correspond to what's happening to the 0 state, and this will happen, that will correspond to what's happening to the 1 state. So in other words, 0 is going to A0 plus B1, and 1 is going to B0 minus A1. So we will get over here, since we have a 0 for the first bit, then this will go into effect, and the 0 in the second bit will go to A0 plus B1. So we could write it like this. Which of course is the same thing as A times 0, 0 plus B times 0, 1. And now what about 0, 1? Where does it go? Well, the 0 for the first bit again means that this will be active, and when 1 is entering this box, it will go to B0 minus A1. B0 minus A1. And so that will be minus B00, excuse me, plus B00 minus A. Well, I'll get it right in the straight. Yeah, this is great. Okay. Plus B00 minus A01. Now notice that all of these predictions here for the action of this circuit agree with what we had wanted to achieve up here. So this we've come up with the correct circuit for this first example, and the matrix describing this this circuit, the matrix describing this circuit is the matrix given here for U1. Now let's look at another example. We'll call this example 2. And here we want to implement a transform that will take 0, 0 to this time, let's say C 0, 0 plus D 1, 1. Okay, so similar to what we have here. Again, if we look at the vectors involved, this means then that 1, 0, 0, 0 will be going to C times 1, 0, 0, 0 plus D times 0, 0, 1, 0. And so again, since we're specifying the action of this transform only on one state, we have freedom as to how to choose what it will do to the other states, but we'd like to make it a two-level unitary transformation, because then we know how to find the circuit for it very easily. So let's choose, in this case, the following. Let's choose we'll call this one U2, and so we'll have U2 of 0, 0 will be equal to C times 0, 0 plus D times 1, 1. U2 of 0, 1 will be 0, 1. U2 of 1, 1 will be, let's make this D times 0, 0 minus C times 1, 1, and U2 of 1, 0 is 1, 0. And if we look at the matrix for this one, we get U2 is equal to, okay, now 0, 0, of course, corresponds to, well, as we've set up here, 0, 0 corresponds to 1, 0, 0, 0, and 1, 1 corresponds to 0, 0, 1, 0. So we will get C, 0, D, 0. The 0, 1 here corresponds to the vector 0, 1, 0, 0. So we get 0, 1, 0, 0. And then for the next one, we'll get D, 0 minus C, 0. And then finally 0, 0, 0, 1. And just as we had a stipulation for the problem above, so we have one here as well. This will be a two-level unitary transformation as long as the magnitude of C squared plus the magnitude of D squared is equal to 1. And now when we do step 2 for this one, step 2 for this one is at least it's non-trivial. Remember now the first state that is non-trivially affected by this transformation is the 0, 0 state. And the second state that is non-trivially affected is the 1, 1 state. And we cannot get from 0, 0 to 1, 1 in one step with a gray code. We need 2 steps. So this one is a little bit more involved than the last one. We could have 0, 0, 0, 1, 1, 1. So here is our gray code for this step. Excuse me, for this problem. And so we to get the circuit now, which is step 3. I didn't even label step 3 above. I could have put it maybe I should have put step 3 here. Step 3. So now if I label step 3 for this one, the first thing we need is a controlled NOT gate that will take us from the 0, 0 state to the 0, 1 state. So we want this. We have a hollow circle up here because we're going from 0, 0 to 0, 1, so the first bit is staying at 0, and then the second one will flip to give us 0, 1. Now that we're at the next to last step in our gray code, we now look at our unitary matrix, and for this case, let's put it over here. U2 tilde is equal to C D D minus C. Now, what bit do we apply this to? Well, in this time, remember we look at, to answer that question, you look at your next to last state and your last state and see what bit they differ in, and these differ in the first state. So this is going to be applied to the first bit, and it will be applied to that first bit when the second bit is equal to 1. So we put a solid circle down here, And so we get U2 tilde. And now we need to undo the action of that C0 gate. So we'll put another one just like it here. And the claim here is that this circuit will implement the transformation shown here. So let's make sure that that's correct. Okay. 0, 0, 0, 1, 1, 1, 1, 0. Let's see where each of those will go. Now with this controlled NOT gate here, that's the first step, and that's going to affect only states that have 0 for the first bit. So the second two states will not be affected by that at all. So we'll get 1, 1 here and 1, 1 here. But for the first two states, what this is going to do, it'll take 0, 0 to 0, 1, because the second bit is getting toggled. And likewise, 0, 1 will go to 0, 0. So this will go 0, 1, and then 0, 0. And now each of these will enter this controlled gate. Now what's happening to the second bit is nothing. The second bit will always be passed through, but the first bit may be altered. It depends on the value of the second bit. When the second bit is 0, nothing happens to the state. So, and this wrote this down incorrectly there. So when the second bit is 0, since this is looking for a 1, when the second bit is 0, nothing happens to the state. So we can say here that 0, 0 will go to 0, 0, and 1, 0 will go to 1, 0. But when the second bit is 1, then the second bit will remain 1, and the first bit will be affected by this. Now again, here's the matrix for U2 tilde, but we need to figure out what the basis is, and look at our gray code. In the next to last step and the last step, we go from 0 to 1. So that means that this matrix is in the usual order. This first column describes the effects of U2 tilde on the 0 vector, and the second column describes the effects of U2 tilde on the 1 vector. So that means that in this first case over here, the 0 is going to go to C0 plus D1, and of course that second bit of 1 here will just go straight on through. And on the other hand, for this one, the 1, looking up here, will go to D0 minus C1. So we have D0 minus C1. And again, the second bit of 1 will pass through. And notice, of course, that that's equal to C01 plus D11. And this is equal to D01 minus C11. And now finally all four of these will go to this final controlled NOT gate. And let's see where everything ends up. Okay, in this last controlled NOT gate, we're looking for a 0 in the first bit. So this C01 will go to C00, but the D11 will stay as D11. The 00 state will go to 01. And down here, similar to what we had up here, the 01 state will go to the 00 state. So we have D00, but the 11 state will be unaffected. So minus C11. And then finally, the 10 state will be unaffected, so we get 10. And now if we compare what we just have here with our desired results, we see that it matches exactly, just as we did up here. I'll check that. So here in this example as well, is acting in exactly the right fashion, and so this will be the correct matrix for this transformation. So that's U2, and here is U1. And now I want to look at one more example, and then we'll tie this all together into an interesting final example. So now, third example, and you can probably guess what's coming. Implement a I said transform up here, and I guess I did. Let's see. Yes, I should say transformation here. And likewise here, transformation. So, implement a transformation that will take zero zero to E 00 plus F 10. And so again, looking at the order of our vectors, we have, this means that 1000 will be going to E times 1000 plus F times 0001. Once again, this transformation is prescribed only for one vector, so we can choose what it does for other vectors, but we want to choose, we would like to choose for it to be a two-level unitary transformation, because we know easily how to get the circuit for that. So let's choose this way. We'll say U3 of 00 is equal to E00 plus F10. U3 of 01 is equal to 01. U3 of 11 is equal to 11. And finally, U3 of 1, 0 will be equal to F 0, 0 minus E 1, 0. And of course the matrix then for this would be U3 is equal to E 0, 0 F 0, 1, 0, 0, 0, 0, 1, 0 F 0, 0 minus E, with the stipulation that this will be a two-level unitary matrix as long as the square root of the magnitude of E squared plus the magnitude of F squared is equal to 1. And so now let's go to step 2 for this one. Now we need a gray code that'll take us from 0, 0 to 1, 0, because 0, 0 is the first non-trivially affected state, and 1, 0 is the second one. And of course this turns out to be very easy. We can get there immediately. Go from 0, 0 to 1, 0. And so our gray code is already done. This is similar in that respect to the first example, except now that it's the first bit that is being changed rather than the second bit. In the example 1, you see here in example 1, it is the second. We have a gray code with only 2 lists in it, but it is the second bit that is changing. In example 2, we had a gray code with 3 lists, and here we're back to a gray code with just 2 lists, but this time it is the first bit that is changing. So since the first state is the same as the next to last state, there's no need for any controlled NOT gates. We just have the following. So step 3, write down the circuit, and okay, we have here U3 tilde is equal to E F F minus E. Yes, okay. And so we need to figure out first on which qubit will U3 tilde act, and it's acting on the first one because that's what's changing. So and we want it to act on that only when the second qubit is equal to 0. And now let's, just as we've been doing in all the other cases, let's check this. Let me, in fact, check something first. Okay. So 0, 0, 0, 1, 1, 1, and 1, 0. We want to see where each one of these will go to check it. This is just like we've been doing with all the other cases. Okay, well, the first thing we can say is that since the second bit is controlling the first one, and it implements the change only when the second bit is equal to 0, then we can immediately say that any state for which the second bit is equal to 1 will be unchanged. So 0, 1 will go to 0, 1, and 1, 1 will go to 1, 1. Now we have to look at 0, 0, and 1, 0. Okay. Now, how does U3 tilde act? What is the basis for it? Well, in this step, this arrow is going to 1, so once again, this will act in just the usual way. In other words, EF will be the way it acts on the 0 state. F minus E will be the way it acts on the 1 state. So, for this first cat, when it comes in 0, 0, now the second 0 is controlling, and the first 0 will go to E0 plus F1. So we'll get E0 plus F1, and then the second 0 just goes right through here, and so we get E times 0, 0 plus F times 1, 0. And then for the last one, 1, this 1 for the first bit will go to F0 minus E1, F0 minus E1, and so that gives us F0, 0 minus E1, 0. And if we compare that, what we've just done here, to the desired action of this transformation, we see that it's acting in exactly the way we wish. So this one is correct, and here we have the matrix for U3. So to review what we've done so far, U1 will take us from 0, 0 to A0, 0 plus B0, 1. U2 will take us from 0, 0 to C0, 0 plus D1, 1. And the final one will take us from 0, 0 to E0, 0 plus F1, 0. So we've looked at all of those possibilities now for two-level unitary transformations. But now let's ask another, and this is a final example, example 4. And we'll word it in exactly the same way. We'll say implement a transformation that will actually I'll be a little bit I'll say a transformation U4 such that U4, now for the moment I'm not going to specify how it acts on zeros, on anything else. But I'll say that the way that it acts on U4 is the following. I'll say that it's equal to square root of 1/10 0, 0 plus square root of 2/10 0, 1 plus square root of 3/10 1, 1 plus square root of 4/10 1, 0. Now let's suppose, so we want a transformation that will take the 0, 0 state to the square root of 1/10 times the 0, 0 state, plus the square root of 2/10 times the 0, 1 state, plus the square root of 3/10 times the 1, 1 state, plus the square root of 4/10 times the 1, 0 state. And we're free to choose how it will act upon the others, but we want this to be a unitary transformation. So let's begin thinking for a moment about the matrix for this. Okay, so in the first column we'll have square root of 1/10, square root of 2/10, square root of 3/10, and finally square root of 4/10. Now, one way we can finish this up is the following. Note that if we fill in the rest of the matrix in the following way, let's make this square root of 2/10, then square root of 3/10, square root of 4/10, and then along the diagonal I'll have minus square root of 1/10 minus square root of 1/10 and minus square root of 1/10, minus square root of 4/10 here, and a positive square root of 4/10 here, and a square root of 3/10 here, and minus square root of 3/10 here, and then finally square root of 2/10 here, and minus square root of 2/10 here. If we choose to fill in the rest of the matrix in that way, now keep in mind once again, this one line is what we really want from our transformation. We don't care about the rest of it, except that we do want it to be unitary, and we'll see why in just a moment. But we want it to be unitary. Well, I'm saying that if we fill in the rest of the matrix in this way, that this is a unitary matrix. Every column has a magnitude of 1. Every row has a magnitude of 1. Every column is orthogonal to all the other columns, and every row is orthogonal to all the other rows. So this is a unitary transformation. And basically what I'm hoping to show here is that we can write this as the product of two-level unitary transformations. And therefore, and each one of the two-level transformations will have the form of either U1 or U2 or U3, and we'll be able to finish this problem. Notice what I'm saying here. Let me make sure you understand. U4 is a unitary transformation, but it's not unitary. Remember that it's not two-level unitary. So, because remember, in a two-level unitary transformation, all but two of the rows will have all zeros and just a 1 in the diagonal. Or to put it another way, for a two-level transformation, a two-level unitary transformation, only two or fewer vectors are affected non-trivially. But this transformation affects all vectors non-trivially. So let's go ahead and write down the information from this matrix up here in our statement of how the transformation acts. So we'll have square root of 2/10, 0, 0, minus square root of 1/10, 0, 1, plus square root of 4/10 1 minus square root of 3/10 1 0. Then the third one will be square root of 3/10 0 0 minus square root of 4/10 0 1 minus square root of 1/10 1 1 plus square root of 2/10 1 0, and then finally square root of 4/10 0 0 plus square root of 3/10 0 1 minus square root of 2/10 1 1 minus square root of 1/10 1 0. So that is the transformation, and as I've already told you now, what we're going to try to do is to figure out how to write that as a product of the two-level unitary transformations. And since this lecture has already gone on now for a bit over 50 minutes, I'm going to leave this question to you. The problems that I will ask will only be on examples 1 or of the type of examples 1, 2, and 3. And in lecture 21, we will resume this example 4 and see how indeed we will be able to use two-level unitary transformations to generate this more general unitary transformation. So let's now look at some problems. Okay, so our two problems for this lecture will be as follows. In the first problem, it's given that A acts on the zero state by transforming it to C times the zero state plus D times the one state, and A acts on the one state by yielding D times the zero state minus C times the one state. So given that information, find the matrix for this circuit. And you see your choices here. A is minus C 0, D 0, 0, 1, 0, 0, D 0, C 0, 0, 0, 0, 1. B is 1, 0, 0, 0, 0, C, D 0, 0, D minus C 0, 0, 0, 0, 1. Choice C is C 0, D 0, 0, 1, 0, 0, D 0 minus C 0, 0, 0, 0, 1. And finally D is 1, 0, 0, 0, 0, C, 0, D, 0, 0, 1, 0, 0, D, 0 minus C. And then for the second problem, if the matrix here, A, B, 0, 0, B minus A, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, you're told that this is a two-level unitary matrix, and also that the magnitude of A is not equal to 1. If given those two pieces of information, which of the following vectors are stabilized by this operator? And the choices are 1, 0, 0, 0, 0, 1, 0, 0 for B, C is 0, 0, 1, 0, and d is 0, 0, 0, 1. E is 0, 0, e to the pi power, pi to the e power. E here is the base of the natural logarithm. So those are the two problems for this lecture. And again, as I said, in the next lecture, we will resume our discussion of example 4. So that concludes lecture 20, and good luck.